The one here, we're going to be spinning, 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 spinning. It's going to be fun. Before we get to spinning, I need to just have a personal trip down memory lane. You ever play with that toy there? You ever play with that toy? Maybe you did it. Maybe it wasn't. Mine didn't look exactly like that. That's fancy. I didn't have that. I didn't have that purple one. Oh man, what I would have. Maybe that toy is familiar to you. Hmm. Sure is familiar to me. I love that thing. Let's see what else we got. Oh, what about this? Now, maybe you didn't have that Fisher Price classic, but maybe you've played this little brain teaser before. Y'all know what that is over there? Yeah, it's the Towers of Hanoi. So the purpose of this game, right, is to move all of the little discs over there that are on that first spindle. You need to move that entire stack to a different spindle. Right? It doesn't matter which one. You just got to move it to another spindle. But the rule is that a bigger disc never gets put on top of a smaller disc. You only can put a smaller disc on top of a bigger disc, and you can only move one at a time. It gets to be pretty tough, I can tell you. There's a nice little algorithm to it. It's once you get down further in there, it gets a little crazy to handle. But maybe you're familiar with that game. I mean, these two toys look very similar, right? I mean, one is just a grown-up version of the other. But again, it's the idea of play. The idea of play opens so many doors to learning. So if you didn't play with either one of these toys, you can go ahead and stop the video now because there's no hope for you in this lesson. Just pick us up next time. Just bail on this lesson. I'm just kidding. I'm kidding. Keep coming. Keep with us. Even if you didn't play with these, keep coming. You're going to try to clarify some things, speak clearly about the mathematics, and we should all be able to get it. What we're going to do is we're going to recognize that the toys, these toys in particular, kind of prepped us for the idea of three-dimensional volume using calculus. You can see the hints that these are stacked little slices on top of one another, and when you stack enough of them together, you get a new three-dimensional shape. You can hear it in the background when you see these pictures. But the idea of spinning a region, we're going to do the same thing that we basically did in the last lesson. So that was lesson 5.3. That was volumes by cross section. We're going to take these infinitely many, infinitely thin slices, but this time the slices have been created through rotation, revolution. The revolution will be televised. So the only possible outcome for the cross-sectional shape would either be a solid disc circle or like a toilet paper roll, like a disc with a disc cut out. That's your book or a lot of things online. Heck, these videos that I'm getting ready to post to you, I'm going to treat those as different lessons, but this is essentially all one and the same. It's this idea of a disc, either just solid or a disc removed from a disc. So it's going to be one minus the other. So in other words, the area of the cross section, in this text that I had with no one in particular, the area of the cross section is always going to have to be some kind of pi times a radius squared. And if you know what a radius is, well, hey, a radius is half the diameter, right? No, the other definition of a radius, which is the distance between the center to the actual circle itself. Because we're going to be rotating around a center spindle, an axis, the length of the radius, we don't want to think about it in terms of half the diameter. We want to think about it in terms of distance between the center of the rotation to the thing that's being rotated. So the radius of the circle is going to be different in different cases, but the big picture of this is we want to integrate that area of the cross section, where the area of the cross section is pi radius squared. So you're going to see a planar region. Now listen, look at this, read carefully here. That says the volume of a solid of a form when a planar region that is adjacent to, what the heck? I know this is English class all of a sudden. Adjacent just means that it's like nestled up right next to the axis of revolution. There's no gap in between the region that we're rotating and the axis that we're rotating around, which is going to produce a solid circle cross section. We're going to use the integral pi times the integral from a to b of the radius function squared. And the radius function is just the distance between the axis of revolution and then the thing that's getting spun around. And if I'm doing things around a vertical axis, so spinning around like the y-axis or some x equals line, then I've got to switch over to terms of y, which is pretty much the story we saw in the last lesson. So let's look at some examples here so you can kind of get your mind wrapped around. Hold on. That was pretty bad. Get your mind wrapped around. Oh. Wah, wah, wah. All right. Again, here's a key thought here, is that the length of the radius is a distance, right? You heard me say that. And distance has to be positive. So it is important here that we use the top minus bottom greatest hit to help us out, or right minus left if I need to be in terms of y. So for every radius that you see, you're going to see you're going to see a distance that is either the function minus the axis or the axis minus the function, depending on which one is on top, or the function minus the axis or the axis minus the function, right minus left, if you're spinning around a vertical axis. So that's just helping you remember this top minus bottom and right minus left routine that we had, but mainly that the radius has to be a distance, so it has to be positive. I know we're squaring it, and I know it's not going to matter, and you can flip them around and still get the right answer, but now set it up where the distance is positive. We're not just scrapping any kind of math on paper and seeing what happened. Now, we're intentional about what we do. All right, so here's what we're going to do. We're going to look at this region R, and this region R is bounded by the x-axis, x equals 4, and then square root of x. We'll see this a couple of times. We're going to take that region and rotate it about the x-axis. So if I spin that about the x-axis, I get this kind of bullet shape. I get this bullet shape. I'll try to draw it here best I can. I mean, we're spinning that whole entire region around the x-axis. It kind of looks like a bullet, if you can imagine what's going on there. Maybe you can. Maybe you can't. It's spinning around. So we got to think about, like, well, what in the heck, how in the heck do we come up with the volume of that solid? Okay, so if we're spinning around the x-axis, there is no gap between the region itself and the axis of revolution. Okay, so that's what I mean by adjacent. It's sandwiched right up next to it. There's no space in between. You can see it pop up there in my drawing. So the volume of the solid, we need to use the disk method, right? So we're rotating around a horizontal axis, so we need to be in terms of x. So we're going to use pi times the integral, and this region lives on 0 to 4 in terms of x, of the radius function squared. And that radius function is the distance between the top function and the axis. So the distance from the axis to the function being spun around. So that would be root x minus 0. So root x becomes the length of the radius. Square that puppy, you get a pretty simple integral. If you ask me, a pretty simple integral, pi times the integral from 0 to 4 of x dx, which I've evaluated for you with the old fundamental theorem of calculus, just in case you wanted to know. 8 pi. So now we're going to take the same region and rotate it around the line x equals 4. So x equals 4 is the boundary, right? It's the right boundary of that region. So we can see how this method is going to be our go-to, right? Because it's butted right up against the axis of revolution. So we need to, because x equals 4 is a vertical line, we need to be over in terms of y. So x equals root, or y equals root x becomes x equals y squared. The region in terms of y lives from 0 to 2. So our limits are going to change. The variable is going to change, but the plan won't. It's still going to be pi times the radius function squared. All right. So here is the idea. Okay. So we're rotating around x equals 4. Boom. That popped right up there. All right. So we get this some kind of like hat or yarmulke looking thing. I'm not really sure what to call that. But how do we come up with the volume of it, right? So again, so pi times the integral from c to d of the radius function squared in terms of y. Right minus left is going to handle the radius distance. Remember, radius is the distance from the center to the thing. So the center is the axis. The thing is the red function. What's that horizontal distance? It's right minus left. So the right side is the axis. The left side is the function. That means the length of the radius is 4 minus y squared. That's the radius. That's what gets squared. We have that pi outside of the definite integral, and there is the definite integral. That would calculate the volume. Okay, rolling right along. Here we go. Let's take a new region. So we'll think about the region that is bounded by y equals sine x, y-axis, and y equals 1. And we're going to be spinning it around a couple different lines. First of all, we're going to spin it around y equals 1. All right, so if we spin it around y equals 1, we get this like, kind of imagine like a little funnel shape or something. I'm drawing it. I promise it's going to pop up here. So there's the two-dimensional region. Oh, did you see that? That scared me. Whew. So there's the two-dimensional region there. So the y equals 1 and the y-axis and the y equals sine x there. And we spin that around y equals 1, we get this that funnel shape. Okay. So again, there is no gap in between the region and the axis of revolution, so we need to use disk method. The cross sections will be solid disks. Oh yeah, big props to my ultimate frisbee players out there. While we're talking about discs, every time I say disc, they're like, "Oh, are we ready? We gonna play?" No, we're not. We're not talking about frisbee here. We're talking about a boring old disc, an infinitely thin disc that builds this three-dimensional region. When we get back together, we'll play some ultimate frisbee. I'm game. Let's do it. So back to the task at hand. We need the disk method. That would be pi times the integral from a to b of the radius function squared dx. And the radius function is that vertical distance between the axis of rotation and the function that's spinning. So the top is our axis, y equals 1. The bottom is the function, y equals sine x. So the vertical distance there of the radius is 1 minus sine x. Boom, pop it in there. Look at the interval. This region lives from 0 to pi over 2. And we fill out the necessary components. We got pi times the integral from 0 to pi over 2 times the quantity, 1 minus sine x squared dx. And that integral would give you the volume of that funnel shape. And I popped that into Desmos. I'm not going to lie. It's kind of boring now because you can integrate it with technology, and that gives me my answer. It tells me what that volume is. Okay, so let's see that same region again. That same region this time is going to be spun around the y-axis. So if we spin this thing around the y-axis, again, we get like a funnel type shape. The drawing's not the best, but it's going to pop in here. Oh, scared me. So we got this like funnel here. We're rotating around a vertical line. So we know we need to be in terms of y. Okay, here we go. This method in terms of y. The region, the axis, they're butted right up against each other. They're adjacent to one another. That's this method in terms of y. You see it there, pi times the integral of the radius function in terms of y squared dy. Okay, so we got to do a couple things. Y equals sine x is not ready. It's not ready. We got to rewrite it in terms of y. So there you go. X is arc sine of y. The domain works out right. We're good there. We're going to write r of the radius function as a right minus left. So the right side is the function. The left side is the axis. So from the axis to the thing. So that would be function minus 0. So just arc sine. Got it. We got the radius function. Pop that in. Recognize that this region lives in terms of y on 0 to 1. It's no longer 0 to pi over 2. That's in terms of x. This is 0 to pi over 0 to 1. So there's our integral. It would be pi times the integral from 0 to 1 of the arc sine of y quantity squared with respect to y. Zip, zap, zoop. Desmos it up. Got it. All right. Okay. Now that that's over, let's see a fun one before we go. Okay. All of these axes of revolution have been straight. What if we make the axis of revolution wiggly? Okay, get ready. We're going to rotate a function around another function. Oh, that's right. You heard me say it. So I got these two functions. I mean, they're pretty crazy looking. Now, I made these up earlier because I knew they would both, it works out right. They intersect at 0 and 4. So we're just going to look on that region 0 to 4. They might not intersect anywhere else. I don't think they do. So here's a picture of what that region looks like. G of x is on top. It's in red, and then the other one's in purple there on the bottom, the quadratic. So we're gonna rotate f, the purple function, around the red function. We're going to rotate the purple function around the red function. So all of these vertical distances here that are going to pop in eventually behind me, right? The red function is serving as a wiggly, like we're going to be stacking circles on this wiggly spindle. So not like a straight up spindle like all the other ones have been, but this is going to be a wiggly spindle. So let's think about this. There's no gap between the region and the axis. So we're using disk method. So we need pi times the integral of a radius function squared with respect to x. Sounds pretty logical. Well, what's the length of the radius? The length of the radius is the distance between the center of rotation to the thing that's being rotated. And if g of x just so happens to be the center of rotation, and f is the thing that's getting rotated, the distance between those two functions is top minus bottom. It's g of x minus f of x. That is the radius length. That's what I can pop in for that radius function. So the integral that calculates the volume of whatever the heck this thing is going to look like is pi times the integral from 0 to 4 of g minus f quantity squared. Here's what that weirdo, whoa, look at that. It's like a dollop of sour cream or something, right? Or like one of the ghosts on Super Mario Brothers or something. I don't know what the heck that's, it's crazy. That's wicked. That's wicked. This is actually an example of Cavalier's principle in action, right? Where you can take a cylinder and just kind of knock it over to its side. As long as the height is the same, they have the same volume, or you can wiggle it. It's still the same volume. We can go into it later. This is just an exciting problem. So we learned to use this disk method. Whenever the region being rotated is adjacent to the axis, we can use this disk method to calculate volume. So there's those formulas one more time. Check them out. Pause the screen if you need to. Next time, we'll talk about what happens when there is a gap. What happens when there is a gap? Is it a brand new method? It's just going to be 2 disk methods for the price of 1. And we're going to call it washer method. So I'll see you in the next one. Peace.